forward to his talk. So please.
Thank you very much, Ivan. Thank you again for inviting me to Japan, to Nara, to Hiroshima. It was really very nice week. I saw a lot, I learned a lot, and I'm looking forward to, thank you all also for coming to my talk. I designed this talk primarily with students in mind, so I hope you can ask questions. I encourage you to ask questions. There's a professor at UCSB who said, not at UCSB, who said it's better to uncover a little than cover a lot. So I am happy to go slow. And I understand that, what you're trying to do here is very interdisciplinary. So, I hope, everybody can follow what I'm saying, but if you can't, please ask questions, right? That's a very important part in science, is to ask questions. So again, this is, I'm mainly a professional email writer by this point, and the actual work was done by, my graduate students and postdocs, and several very, capable and knowledgeable collaborators, Christina Marchetti and Seth Fraden. And this work is really all due to them, right? And so, oops. Somehow the slide advancers don't like me.
Maybe.
No. Okay, I just needed to click. Okay, so what I want to tell you about is, almost a dozen years ago, we developed what I would call an active fluid. And I'll briefly summarize these active fluids, and then I'll tell you how can you build interesting materials that do really kind of unique things with these active fluids, right? And what do I mean by an active fluid? Usually, if you're a physicist or a chemist, you've learned about thermodynamics. And if you have passive molecules, you know that these molecules exhibit Brownian motion, and you can define such a thing as a free energy, and the system will always minimize free energy. What we are studying is a collection of microscopic active molecules. These are molecules that consume ATP and generate local forces and motions, and therefore they are distinctly out of equilibrium in many ways that I am out of equilibrium. I'm also consuming energy because, I ate a very nice lunch today. If I don't eat for a week or so, bad things happen, right? And so hopefully this will become obvious as I go on, right? And so our experiments are really, I'm a physicist by training, and physicists really want to have control, right? If I look into the biology, the world is very complicated in biology. It's hard to exert that control, right? And so what we do is we essentially do, we are quintessential, paradigm of an active material, right? Humans are an amazing things, but we are also extremely complicated. And what we do is a little bit of a Frankenstein experiment. So what we want to do is we want to isolate the building blocks that make cells able to do what they do, and start putting them together from the bottom up, and then see how complexity arises in the systems. So what are the building blocks that we use? One of them is a microtubule. Microtubule is a polymer. It's 20 nanometers in diameter. It's 1 micron in length. And you actually do these, you purify these things by actually extracting it from a brain tissue. So we have to go to the slaughterhouse, and after a day of hard work, you get lots of these tubules that are just tracks. The second, and this is really the essential component, this is called the kinesin molecular motor. This is a protein. This is about 4 nanometers. Each one of these heads can bind to a microtubule. It binds to a microtubule. It hydrolyzes ATP. It takes an 8 nanometer step every 10 milliseconds. And so over a second, it can take about 1,000 steps, and it can move about 1 micron, 1,000 nanometers, and it can generate forces up to 5 piconewtons, right? And so this really is a marvel of biology, right? This is the smallest, very efficient motor at a microscopic length scales. And then we, so those.
I can ask a question?
Yes, sure, yes,
Why
yes.
does it do that? What is it?
Because oftentimes you need to, move things around in a, if we were just to wait for a diffusion is extremely inefficient, and if you wait for, your diffusion for the stuff to diffuse from, your brain to, the synapse in your arm, that would take a long time, right? So you need to have active transport, right? And a similar motor, a different category is what powers, I'm speaking now, and I'm speaking because there's these molecular motors that, are consuming ATP, taking many, many steps and contracting my muscle, right? And it really enables all of the mechanical motions of the cells, tissues, and entire organisms, right? What we do is we add a depleting agent. Depleting agent is a polymer that induces an attractive interaction between two microtubules and brings them together. And then when you add all of these things together, you create an elemental building block, right? So now you have parallel microtubules. What can happen is that a cluster of motors will land on these microtubules. This motor will walk towards this plus end. This motor will walk towards this plus end, and because of Newton's third law, is it the third law? I think so, right? I forget. You'll get sliding of the microtubules, right? And that generates local active motion. And you can actually observe that under a microscope. This is one microtubule, this is a second microtubule. In absence of activity, when these microtubules come, they minimize their energy and they would just sit there. But what you can see over here is that two microtubules come together. And at this point, you can't see the motors. The motors are there. They push them apart. And that, initiates, while they're pushed apart, there is a molecular force being generated. And what we did, a dozen years ago, is you've taken, just to give you a sense of scale, this is probably 5 microns, right? So this is really very zoomed in. We've just increased the concentration of these filaments and looked at a very zoomed out region, right? So this is a millimeter size scale. And you see that you create, this is, 1,000 times higher concentration of filaments. And this is what you observe, right? Is you observe a very turbulent-like dynamics that looks really quite intriguing, right? And again, all of these, this is a millimeter, this is a large piece of experimental crud, and this is probably 50 microns in size that in a passive solution would just sit at the bottom of your microscope chamber and not move. Here, because the flows are being generated, the flows are pushing this thing around on a time scale. This is probably sped up 10 times or something like that. Okay, so this is an interesting out of equilibrium material that is consuming ATP and generating these large scale motion, right? And this is very different from kind of classical turbulence, right? If you boil your pot of water, you'll get convective flows, and that's because you're putting the energy to the boundary. Here, you're putting the energy into the system from a microscopic length scale. Does that make sense? Students? Yes? Any questions? And the nice thing from a physics perspective is this is the flows. The flows can reach tens of microns, but you have an energy regenerating system. This is ours, and you can keep this going up for 120 hours, right? So, you can really do 120 hours allows you to take a lot of data, right? So you can do some nice experiments. Yes.
How does it look like the experiment? Is it in between?
This is a quasi two. Yeah. This is a little slab between two slabs, so maybe 100 microns thick. But we can do different geometries, and I'll tell a little bit about that, right? what's happening if we zoom in, right? Now I've zoomed in, and this is maybe 100 microns, sorry, so I'm missing some scale bars. And now since we have a higher concentration, we have a system of these bundles, and then you can see what's happening in this movie. What's actually, if I think it would be better if I can zoom this. Is it going? No, it's not going. Okay. You know, you can see now the bundles cannot just extend because they are clamped at their ends. And what's happening here is that as a bundle extends, it's clamped here, here probably, and it buckles. And once it buckles, it breaks. And then it reforms with another bundle. And so what's happening is now you have like a classical gel, but in this classical gel, the bundle is constantly extending, breaking, reforming. And this kind of cascade continues as long as you have ATP. Once the ATP runs out, the system just becomes like a really, really soft passive jello. And so this is a useful thing. So for example, what we've done here is you can take, instead of looking at microtubules, now we have just passive beads, right? Passive beads tell you what's happening to the fluid flow, right? And so, again, because we've built the system from the ground up, you can change the ATP concentration. That changes how fast your motors are working, and that changes the fluid flows. For example, here, the beads are just passive because your network is passive. There's no chemical fuel. Here, this is saturating ATP, and these beads are, just being more or less advected by the fluid and pushed around by the flow, right? And you can quantify that. Now, if you are in kind of soft condensed matter physics, if I put a microscopic colloid in a solution, it's going to exhibit a Brownian motion. And the way you characterize that is you measure a mean square displacement, right? And then you find out how the mean square displacement, increases with time. And if I'm, constantly changing directions, I'm not going very far, right? And so the mean square displacement in a classical fluid would increase, mean square displacement has units of distance squared. This is time. So the mean square displacement would increase linearly with time. That means diffusion is very inefficient in moving things around. And at zero ATP concentration, you can see that these things are actually exhibiting even, oops, I have to admit people are. You can do it? Okay. All right. And I'm not monitoring if there's questions on Zoom. Just can somebody let me know? Or but then at highest ATP concentrations, you can see that you start, this is squared. So distance squared increases with time squared. And that means that they are moving ballistically, right? Essentially for this over this length scales, right? So you can control the motion and things like that. What is the basic for, what drives this dynamics, right? So here we've changed our system just a little bit in that we've sheared aligned the system. So initially, all of the microtubules are aligned along this direction, right? And this is a much denser system. And what you can observe here is that as soon as we let the system go, it develops this instability, and this instability grows over time. This was theoretically predicted 10 years before it was experimentally observed. So theoreticians, can do useful things. Sorry. This really motivated us to do these kind of experiments. What's unique about the system is usually, this is almost an nematic liquid crystal. What's unique is usually if you take a material and if you bend it, what does the classical material want to do? It wants to become straight again, right? Here, what's happening is that you have active stress, and this active stress depends on the differences or active force on the differences. This is the local alignment. And so you will create local force if you create differences in stress, if you create differences in alignment. So this is a very unique material in which if you bend something, it wants to bend more. right? And that leads to a lot of interesting phenomenology that can be used to study interesting, create interesting material with interesting dynamical properties. Yes.
At the beginning, we have a feeling that this is a collective behavior.
Yes.
And then at the end, it becomes disordered.
Yes, this thing melts into an isotropic. You initially start with a nematic, and then it melts into an isotropic. But what you can do actually, what you can do is you can create such a high concentration of these tubules that you get what's called, a liquid crystal, right? That Ivan studies, and that ubiquitous material. You can see here that there is this liquid crystal, and this liquid crystal, you can see that there is this bend, initial bend. And what happens over time is that this bend, again, self-amplifies, and at some point, it becomes so, the gradients become so sharp that you no longer can create a uniform field, and you create a fracture line, right? And so, for example, here, right, there's an orientation that can be defined here, there's an orientation that can be defined here, but there's a local fracture line, and it's terminated by these two singular points that we, in liquid crystal literature, would call a topological defect, right? And so in a very dense nematic microtubules, this is now in a quasi-2D situation, these things would form this kind of self-propagating instability that generates defects, right? On the other hand, if you're just generating defects all the time, that is not very good. The other process that can happen is that you can have this defect, and this is a defect of charge 1/2 and minus 1/2, and they can come together and self-annihilate. And so here you have this singularity, here you have this singularity, and here the singularity vanishes, and the field becomes uniform and defect-free. Okay? This results, let me just, again, Ivan is, if I click here, then, so this is what I've told you about, these are the lowest energy defects in a liquid crystalline direction, right? What happens here is I say that this has a topological charge of 1/2, because what happens when I go around the core of this defect? This black rod can go around the core of this defect, right? And what's going to happen is by how much did it rotate? By 180 degrees. If it rotated by 360, I would say there's a charge of +1. This rotates by 180 degrees. So this has a charge +1. This has a charge of -1/2. You can see that this one is symmetric and this one is not symmetric. And so those, the stresses generated here are not balanced. The stresses generated here are balanced. And what you can see here is that you result in what's called an active nematic liquid crystal, right? You get this dynamics. For example, you have two defects over here, right? So, these defects are continuously being generated. You can see here creation of two defects. I think that there's going to be, again, if this movie loops, there's going to be this defect, this defect, these defects. I don't think they don't come together, but you're creating more defects here, and this leads to this kind of unique turbulent-like state. At this point, are there any questions from students? Does this make sense? Again, please ask, I'm always, I'm always also afraid of asking questions too, but, yes.
If it was not active matter,
yes,
what would happen?
There's a lot of elastic energy here, and if you have, no boundary conditions, all of these defects would gonna minimize elastic energy, and they would self-annihilate.
Make
A uniform.
kind of lattice or something?
No, they would just make a uniform liquid crystal, right? You need to do things like put in colloids or things like that that perturb the boundary condition to make defects stable, right? These are point-like defects. This is a quasi two-dimensional sample. Something we've done in the past is we've actually looked at a three-dimensional system. And so and you can imagine in a three-dimensional system, these defects would, these are now point-like structures. In 3D, they would become what's called a disclination loop, right? And this is, we've used light sheet imaging. And here you can see that all of these things, you create this tangled network of these three-dimensional loops that span your sample. Sometimes these things close up on themselves, as is shown over here, but they do all kinds of other interesting things. And this really is a talk onto itself that, the dynamics of understanding and classifying these kind of topological defects it's a rich dynamics that really remains largely unexplored, right? You can see here, anyways. So what I told you about now is active fluids powered by the molecular motors, right? These are turbulent, tunable, and robust turbulent-like flows that are powered in a different way that usual turbulent flows are powered. They really are not conventionally turbulent because there's a finite length scale. They exhibit this long-lived non-equilibrium dynamics, hours and days, and they're very robust materials, right? What I can do in Santa Barbara is I can freeze this material, put it on dry ice, ship it to Hiroshima. You come here, you thaw it at 0 degrees, and that will just continue doing its thing until it, and you can make a milliliter of the sample without a problem. Okay, so what I want to tell you about in the rest of the talk is how we use these active fluids. What are the active fluids good for? They're good for moving things around, right? If you want to move things from point A to point B, that's what active fluids are, controlling motion on microscopic scale. So what I want to tell you about today is, in the second half of my talk, is how we use these active fluids to control soft interfaces and how we use them to control elastic gels, build and control elastic gels, right? And so this is, for example, one quick example, right? Is here we have an oil, water, we have an active fluid at the oil-water interface, and we put a little inclusion over here, right? This is, again, not hundreds of microns inclusion, and this is your active pneumatic, and you can see that this inclusion is exhibiting interesting dynamics, right? If you notice what's happening here, this inclusion has chirality to it, and you can see that it's always rotating in one direction, right? So you are harnessing here the motion of a active fluid, turbulent-like motion, to generate persistent rotation in time, right? And so these are, for example, 4 different inclusions that we looked at, right? It's not so surprising if the inclusion is achiral, it's going to move around, but it's not going to rotate in any fixed direction. But if inclusion is chiral, and if it has this 2 chiral notches, 6 chiral notches, it's going to preferentially rotate in one direction, right? So it's a little kind of engine. Here you can see what's happening, right? Is there's a topological defect, it's nucleated, it pushes onto this notch, and then it goes in this direction. Oh, this is not looped, right? And then, that creates a different defect. And so you get this cycling of defects that is influenced by the shape of the inclusion, and that leads to the rotation. So here, for example, you can see a defect comes over here, it hits the boundary, it's pushed upward, and then this creates a bend instability that creates another defect, and so that keeps cycling, and that keeps propagating the dynamics of your inclusion. Okay? Yes?
Why is the energy fluid inducing the flow?
That again is coming from these molecular motors, right? So that's all chemical energy that's being, and the motors are converting that chemical energy into motion that pushes the microtubules apart. Yeah, in this case, this background is still an active nematic that I've described before, right? The only thing that I've done is I've changed boundary conditions by putting this inclusion, right? And what you observe is that there's really delicate interplay between this complex chiral boundary and the, inclusion shape and the dynamics of topological defects, right? And so I think this is a very rich playground to explore. Yes.
So concerning this defect, the blue and the red in the curve.
Yes.
I would expect naively that the red is more efficient to turn because it has 6 teeth. I don't know.
Yeah.
And the blue does the same,
Yes. No.
Even a single one. I don't know what could happen.
Yeah. Even one is sufficiently good to, that certainly came as a surprise to us,
It's
right?
not intuitive.
No, it's not. But I mean, this remains to be studied theoretically, right? This was just experiments from last year, right?
There's a question from the audience online.
Okay, great. There's also a question back there.
Yeah. Hello.
Okay. Yes, online. Yes, please.
Yes. Yeah, it's a very interesting work. If we have two kinds of defects,
Yes.
so you are introducing only one defect.
Yes.
So if there are two defects, what will happen?
We have no idea. Again, like I think that there's a lot to do here, right? Is you could imagine creating an array of crystals, right? And putting an active nematic, and all of them are turning, and there could be some frustration. I have no idea, I mean, this is very much a beginning, not the end of these kind of experiments, right?
So two defects should talk with each other or align with each other.
Two inclusions.
Okay, two inclusions. Yeah.
Yeah, there's interesting, like if inclusions are square-like, they'll really stick together, right? And if they are spherical, they don't want to stick together, right? There's effective kind of interactions between these inclusions. All very good questions. I have no answers.
Okay,
Sorry.
thank you. Yeah, thank you.
But there was a question there. You mean control the XY movement? We are working on that, yes, and because we can make these things light responsive, but we are not there yet. That would be interesting. Great question. All right, let me, tell you a little bit about something that's related to this, right? Is, what we wanted to do next is this is a rigid interface. We wanted to explore how this fluid interacts with a soft, flexible interface. So here you have polyethylene glycol and dextran. These are two polymers. Two polymers, as a rule, will phase separate, just like oil and water will phase separate. And this is your phase diagram, right? This is the concentration of dextran. This is the concentration of PEG. If I make a sample here, you'll get one single phase. If I make a sample in this yellow region, you'll get a PEG-rich phase and a dextran-rich phase. This is something that biologists, engineers know very well. Recently, even, this kind of phase separation seems to play a really important role in cell biology. Of course, physicists knew about this for a long time, right? Now, what was a surprise to us is what we did is we now took two of these phases, phase separated them. So this is a dextran-rich phase. This is a PEG-rich phase. This is very much like if you prepare a vinegar, oil, a European-style salad dressing. You mix oil and water, they phase separate. But then we added microtubules in here, and you can see that the microtubules effectively only go into the dextran-rich phase. And in a dextran-rich phase, generate flows. Now, why is this interesting? Because when you have a salad dressing, what happens, right? Is if you shake the salad dressing, that's how you'll break up the interface and create very small droplets, right? Here, we have something that generates fluid flows that could influence the dynamics of something that we know very well, phase separation, right? So let's look what happens, right? So this is our experiment here, right? We use something that's called a light sheet microscopy. This is a 2 millimeter sample, for example, over here. And what you can observe here is that, you know, again, this is, we waited for a while. The dextran phase separated to the bottom. There's active fluid here, right? You can see it, there's microtubules here. And this is a passive polyethylene glycol phase, okay? Are there any questions about, and then we look from the side, there's some kind of imaging things, but you know. Are there any questions about the experimental setup? Again, this is what you're seeing, right? Microtubule generated three-dimensional active fluid over here, passive fluid over here. This is 200 microns, right? If you were just to create an oil-water interface, this oil-water interface would be almost perfectly flat, right? There would be some thermal fluctuations. It might be rough of the order of nanometers or so, right? What you observe here is that its interface is very, very rough. And this is how the movie looks like, right? You can see this interface. This interface is exhibiting this giant fluctuations. You can see these things with your naked eye. You essentially don't need a microscope. It's of the order of 100 microns, right? And so what's happening here is you're generating a fluid, the fluid's generating flows, and the flows are pushing onto the interface, right? And generating these large-scale distortions. Now, if you look at this interface, it looks a little bit funny, and this took us a while to understand, but you see you have, you know, regions, you have the hills and the valleys. The valleys have positive curvature, the hills have negative curvature. That's just how we define curvature in this quasi-2D system. And you can see that the valleys are usually very, very deep. The hills are very shallow and round. There is an asymmetry in the system.
With gravitation?
No,
No.
we can, you know, we can do a simulation where we turn the gravitation off and you still see the asymmetry, right? And you can quantify what is the probability of observing a certain curvature. Again, this is the valleys. You know, you have some finite probability of observing a curvature of 0.04. If you have the hill, the probability of observing a curvature is minus 0.04 is 0, right? And so we don't know exactly what's happening here, but you know, with Christina, and again, we've started a collaboration, and there's hints what's happening, right? What's happening is this is your nematic field. Again, this comes from the theory that seems to reproduce qualitatively the asymmetry. What you're observing here is you can see that this is a -1/2 type of a defect, right? And can you see where there's a valley over here, over here, over here? There's always a -1/2 defect associated with it. And there's a +1/2 defect, right? That usually is associated with this shallow, long hills, right? So in a certain way, this is an even richer system because we have a flexible interface. And this flexible interface is deformed by the defects and is generating defects, right? This is, you know, the experiments are in 3D, the simulations are in 2D. In 3D, the defects are going to be much more complicated. But this is something that, you know, I think is, you know, that we are working on right now and trying to understand in more detail. Again, you know, that's a schematic over there, right? What you can do is you can do something more dramatic, and you can simply decrease the effective interfacial tension. And what you observe is, again, that the interface now becomes extremely violent, and it starts to disintegrate. And essentially, you can see that there is peg droplets that are starting to be enveloped by this active fluid, right? And over time, if I speed this up, I don't know if I can speed it up, you see that you start to create more and more of these passive droplets that are being enveloped in an active fluid. Notice that almost never do we observe an active fluid that's being ejected into the passive into the passive phase? So there's this asymmetry persists, right? Deformations increase over time, and you end up in this kind of funny perforated material where you have no dextrans over here, but you have numerous PEG droplets over here, right? What's happening here is probably very complicated because you have a ton of interfaces, you have a pneumatic director that's going all over the place, and you know, this is again something that we hope to study in the future. Here you can see a specific event, for example, I think, oops. You know, here is a three-dimensional interface, and you know, I hope I can play this movie. You know, here you can see the interface. You can see this creation of a very deep valley that protrudes outside and closes into a PEG-rich droplet, right? And that's shown over here.
And it's stable.
The droplets are stable, yes.
Line.
Yeah, no, and they actually, you know, they can go back into the PEG phase, but they can never merge with one another. And so there is a thing called asymmetric in viscoelastic fluids. There is viscoelastic fluids phase separate very differently than normal fluids. And, you know, actually Professor Tanaka at Tokyo is a world expert on this. And I think there's interesting analogies between this phase separation and what he's been studying. Are there any more questions from students in particular? Or yes, please.
Go inside and go out is the same.
No, because you are accumulating. You start with something where there's very few droplets, and there's many, many droplets that are being generated and are being embedded in a fluid. And the reverse thing happens very rarely. And so over time, you're building the concentration of the droplets and building this kind of heterogeneous material. Yeah, the issue is that at some point we run out of energy and we never reach a steady state. We could probably do something more fancy where we exchange ATP more, but you know, we have not done that yet. Yes.
Do you have any information about concentration of active phase? Because interfacial energy is always determined by the impurity of the materials.
Yes.
So your active material is kind of impure, you know, substrate.
Yes.
Solving the defection phase.
Yes.
I think that the same concentration participating in the structure appearing actively in interface.
I think what's interesting is that there is what we believe is happening, we haven't measured, is the interface is used to align the liquid crystal next to it, right? And that generates interesting active stresses, right?
When you reduce concentration, liquid crystal phase it disappears.
Say that again?
When you decrease the concentration.
Yes. This actually, if I kill the activity, this would be an isotropic phase. But if I increase the activity induces flows, that induces the alignment, that it induces a liquid crystalline phase. You know, we can also go into a quasi two-dimensional geometry. So you see, for example, here, right, you have a quasi 2D geometry. This is just normal coalescence over time. You know, at low activities, what you observe is that the coalescence is much faster. What's happening here is the droplets are passive. It takes a long time for these droplets to find each other. With the activity, they become a little bit more mobile. And at the same time, they become, you know, much larger, right, than compared to this. If you add even more activity, what happens is that interfacial tension is so rough that you will observe over time, these droplets start splitting apart, right? So usually in a passive liquid-liquid phase separation, the droplets always increase in time until you get a bulk phase separation. Here, you can actually create a steady state, and you can see that's probably better on this movie, right, is you start with a very large droplet. It has huge interfacial tension fluctuations. And at some point, you see there's breakup into smaller droplets, and then you reach a finite droplet size, right, where you balance the rate at which the droplets come together and droplets fall apart. There's, one other thing that we observed in this active liquid phase separation that was quite surprising and unexpected, right? What you observe here is, again, in a classical fluid, right? There's going to be an interface. It interacts with the substrate, and there's a balance of forces. And this balance of forces determines what's called the wetting angle. And controlling this wetting angle has a lot of important technological applications, right? Here, for example, you have an active fluid, and you can see what happens to this active interface, right? Again, this is a wall, this is a peg phase, this is a dextran phase. What you can observe here is that the active fluid starts climbing along the wall. Huh?
That's like superfluid.
Well, but in a so why is this happening, right? What we believe is happening is that you have a wall. The wall aligns the microtubules. The microtubules provide an extra force. The microtubules extending provide an extra force, and that propels the droplet to climb along the wall, right? And that's what you can actually see that in this movie more dramatically. Here you can see there's a peg dextran interface. We've made this very short. So this is now peg water interface. And you can see that the fluid starts climbing along the wall and accumulating along the air-water interface. You can see that there is these traveling waves propagating along the air-water interface, and you start accumulating more and more water over here, right? I mean, more and more of active phase. And then at some point, you'll accumulate so much of an active phase that you'll get a droplet that falls down. And so you get this kind of recirculation mechanism, right? Again, like in a certain way, very loosely, there's this fountain effect in superfluid helium, right? Where the superfluid helium goes along the walls. This is, very different physics, but, still somewhat, evocative, let's say, right? You can take a droplet at low peg concentration over here, as it's shown. And then you can take a droplet at high peg concentration. And you can see that this droplet, again, at low peg concentration has a very well-defined angle, right? And then as you add activity, what happens is activity starts to spread the droplet around, right? And this, in a certain way, is very reminiscent, it opens new intriguing possibilities, right? What you would want to do, for example, is create a droplet that would have an angle on one side, this angle, and on the other side, this protruding angle and retracting angle. If you could do that, then this droplet would start crawling along the surface, and that actually is the simplest model of motile cells. So how can we do that, right? So what I told you, again, I'll be finished very soon, is, usually we create these motors with a streptavidin linker, and, you create these forces, and these forces are continuously being generated. What we've done recently is we've learned some biology, done some molecular engineering, and used something that's called an optogenetic domain. An optogenetic domain is just two proteins isolated from a plant. People use it in biology all the time. I don't know if you've ever seen this, but it's a little bit scary. You have these optogenetically engineered mice, and you shine light, and they start running, and then they stop running as soon as we don't do anything as dramatic, but these things work really well. You shine light, the cluster forms, and then you generate you shine light, you form a cluster, you generate force, you take light off, and then this light cluster falls apart and nothing happens, right? And now what you can do is you can actually generate, there's off light, we shine light on, you start generating flows, right? And then you take light off, within 20 seconds, the whole thing stops. You turn light on, this dynamic starts again. And this is very robust, and you can repeat this many, many times. Again, this is your response function, the speed, within 20 seconds, you can shut this fluid on and off. And now this creates a very intriguing possibility of creating artificial, usually what a cell does is it crawls, it senses its surface and decides I want to go in the X or the Y direction. We can't do that, right? But what you could do is you could look at this droplet, right? And you could say that, you know, can I pattern the stresses in the droplet in such a way that the droplet, you know, divides into two, that the droplet starts crawling in a certain direction? And you would probably need to do that in a feedback-based mechanism, right? So that's our future aspiration, our future goal. You know, I mean, it's always good to have future things in mind. And so that's the active liquid-liquid phase separation, and how just adding activity, we've taken something that people, physicists, chemists have studied for 50 years, added activity, and it really changes things in kind of really deeply fundamental ways, right? Let me just, 5 minutes, I'll stop in 5 minutes. There are a few questions. Let me show you something that's perhaps even more intriguing. What we start here is we start with a bunch of actin bundles. Now, actin bundle has no motors. You can think of this as being just a very, very soft gel-like material. It's a cross-linked network. It's a soft elastic solid. What we do is we mix this soft elastic solid with an activity, right, to create an active gel. And we create initially what I would call an active composite, right? And this is your initial state, right? This is your microtubule bundles are in blue, the actin network. The microtubule bundles will generate fluid flow. The red is the actin network, and the actin network, you can think of these are very, very large Velcro-like rods, right? They're not initially overlapping with one another, but when the fluid pushes them together, what's going to happen is rods will come together and stick. And so you'll rearrange the network with the activity. And this is what you see, right? This is now a quasi 2D projection. This is your actin filaments. And then we just initiate, this without activity. These things are 50 microns long. They would just sit there forever, right? Then we initiate activity. And what you observe is that you are restructuring the network and creating an entirely different kind of structure, right? You can see here is I get these nodes, I'm creating and assembling a soft elastic material that's being driven not by thermal motion, by the activity of the fluid that you cannot see. What you observe in the Z direction, right? So this is X, Y, Z, right? But so I'm looking here at from above. This should be Z, this is Y. So now I'm looking on the side, and what you see on the side is that you create actually this network contracts in a X, Y, in this direction. So what you're assembling is a soft, elastic, membrane-like material. Again, this might be more intuitive over here. Again, you can see the actin, the microtubules are pushing the actin, and you start creating this soft elastic network, this soft elastic membrane. If you zoom out, this is 100 microns by 100 microns. This is 300 microns by 300 microns. And now I'm just showing you the membrane. And this is a membrane. This is like a very thin elastic sheet that is exhibiting these very giant out of plane Z fluctuations, right? Now, people have studied the mechanics of soft elastic sheets extensively. People like David Nelson, who was here in NARA, and many other people, right? And a lot is known about, passive mechanics of active sheet, but these are active mechanics of active sheets. Now, this is 300 microns by 300 microns, and something really remarkable happens when you zoom out. And now we are looking again back in X, Y. This is 3 millimeters. This is, we can make this centimeter-like samples. And what you observe is you create this soft elastic network. And then this soft elastic network generates spontaneous, large scale, by eye visible shear modes. This thing just starts shearing left and right. And somehow you're exciting this non-equilibrium crystal at microscopic length scales, and this motion is being coordinated over millimeter size length scale, and you can see that the strain becomes so large that you get these folding patterns over here, right? And this thing really starts, doing kind of completely unexpected things, right? And for students, this was actually something that we completely didn't expect. My student was trying to do something else, and we stored a material in a wrong way that cross-linked actin. And the student said, comes back to my office and says, "Oh, the experiment didn't work. This is terrible." And I'm like, "What do you mean? This worked beautifully. It's not what we wanted, but you should always keep an eye. Oftentimes in science, you're not gonna, you're gonna look for X, but you shouldn't, and if you find X, that's great, but sometimes you observe all of these great things that, that just happened because, we didn't anticipate it, right? So this is, for example, just another movie. Here we've introduced crosslinker in only half the sample, right? And here there's no crosslinker. And so you create this elastic network, and this elastic network starts exhibiting these kind of, instead of shear modes, you start creating these kind of autonomous bending modes, right? And this really starts to look at something like a biology, right? You could imagine that this is like some kind of animal-like that's about to take off and swim off into a pond or something like that. With that, I'm really out of time. I think I've convinced you that active fluids are interesting, and there's a lot of things where we really don't understand what's happening. We're just starting to, this is a ground zero of our, there's still, a lot of phenomena to be discovered, but even more importantly, what we need to do is we need to develop theories that can tell experiments that can make predictions that we can test, right? Right now, we are just mixing things in a tube. Thank you very much for your attention, and I'm happy to take any other questions.